In these example problems, we're going to look at things where there's a little bit more going on than in some of the last problems that we've had. And so, in this problem, we have a person who has a tractor and he's pulling a bunch of firewood along the ground. And so this is something where we have the tension in the chain, we have the weight of the sled, we have the angle that the tension is pulling at, but we also have friction acting. So we're told that the coefficient of friction between the sled and the ground is 0.3. And so we're given this diagram just to kind of redraw the free body diagram. We have the force of gravity acting. We're told that the weight is 14,700 newtons. We're also told that the chain is pulling with a force of 5,000 newtons at an angle of 40 degrees. So that's this angle right here. That was this pull. We had this weight. We also have the normal force acting. Which we will calculate momentarily. And we have the force of kinetic friction acting against the motion. Okay, later on I'm going to need this, but if I know the weight of the object, I also know its mass. The mass is 14,700 divided by 9.8. And so later when I go to find the speed of the object, I'm going to need this mass. So just to calculate it, 14,700 divided by 9.8 gives a mass of 1,500 kilograms. So again, sometimes you're given the mass of an object and you have to multiply by 9.8 to get the weight. Sometimes you're given the weight and you divide by 9.8 to get the mass. Okay, so to find what the normal force is, which we need to be able to find the force of friction, we have to break the tension in the chain into components. We have to find the x and y components of this tension. The x component of the tension will be 5,000 times the cosine of 40 degrees, which is 3,830.222 newtons. The y component of the tension will be 5,000 times the sine of 40 degrees, which is 3,213.938 newtons. To find the normal force, we have that the forces acting upwards have to balance the forces acting downwards. So the normal force plus the y component of the tension has to equal the force of gravity. So the normal force plus 3,213.938 has to equal 14,700 newtons, which gives a normal force of 11,486.062 newtons. And then finally, to get this force of friction, it's the coefficient of friction times the normal force, which would be 0.3 times 11,486.062. So the force of friction is 3,445.806 newtons. Okay, so we're asked to find the work done by each of the forces individually, and then the total work done. So again, in this problem, the normal force and the force of gravity don't do any work. At first, it would make it seem like we don't need to calculate the normal force, but since there's friction, we needed that value to be able to find the force of friction. So first, to find the work done by the tractor, it would be the parallel component of that force, the component that's parallel to the motion. So that's Tx is 3,830.222 newtons. And we're told that it slides 20 meters. So the work done by that pull is 76,604.44 joules. The work done by gravity and the work done by the normal force, I said that both of those are 0. Again, if the force is perpendicular to the displacement, that force does 0 work. Finally, the work done by friction. First of all, the work done by friction is going to be negative because the force of friction is acting to the left. This slides to the right. So if a force opposes the motion of an object, it does negative work. It's taking energy away from the object. So it's negative, and it's the force of friction, 3,445.806 newtons times 20 meters. So that's negative 68,916.12 joules. Then we were asked to find the total work done by all of the forces, the net work done. So that would be the work done by the tractor, plus the work done by gravity, plus the work done by the normal force, plus the work done by friction. Again, if there's 4 forces acting, I need to find the work done by each of those 4 forces. Several of them were 0. So I have positive 76,604.44 joules. The work done by gravity was 0. The work done by the normal force was 0. The work done by friction was negative 68,916.12 joules. And so if I add all those together, the total work done is 7,688.32 joules. Part B says, if the sled starts with a speed of 2 meters per second, calculate its speed at the end of the 20 meters. So we're going to do this one using work and energy. You could also use kinematics for this. But for this, since we already calculated this net work done, this net work equals the change in kinetic energy. So I know that 7,688.32 joules will equal 1/2 times the mass of the sled. So that's why we found the 1,500 kilograms times the final speed squared minus 1/2 times the mass, 1,500 kilograms, times the initial speed squared. And it starts with a speed of 2 meters per second. Again, a common mistake that people make is they just set the final kinetic energy equal to the work done. That's not always true. If it started with some energy, then the work just adds on to that energy. You have to remember to include that initial energy. And so if you solve this, you get a speed of 3.775 meters per second. So you'd find that initial kinetic energy, add it to the work that's done. So bring it over to the left-hand side. You get 10,688.32. You set that equal to 750 v squared, 1/2 times 1,500 times v squared. And you get this speed of 3.775 meters per second after taking the square root. Okay. This next problem is one that looks a little bit complicated, but actually ends up being somewhat simple. So we have a 1,860 kilogram pile driver that's being dropped on a steel I-beam and trying to drive it into the ground. So that beam is sitting on the ground. The pile driver falls 8 meters before contacting the beam. and then pushes the beam 0.25 meters into the ground before coming to rest. So the top of the beam is going to move down an additional 0.25 meters. So that'll be the new height of the beam. And we're going to find the magnitude of the average force that the beam exerts on the pile driver while the pile driver is being brought to rest. So the key idea in this problem is that this pile driver is starting from rest. It's being dropped to the ground. And then it hits the pile driver, or hits the beam. It's moving when it hits the beam, but it pushes the beam down, and eventually the final speed of the pile driver is also 0. And so this means that the change in kinetic energy of the beam is 0 from the very beginning to the very end. It doesn't mean that it wasn't moving at all during the trip, but the speed at the beginning and the speed at the end end up being the same. And so what that means is gravity was adding energy to this, but when it hits the beam starts to take energy away from it, and eventually the total energy added to this is 0. Again, the change in kinetic energy is 0, which means that the total work, or the net work done, which is the change in kinetic energy, must be 0. And that's the work done by gravity plus the work done by the beam. So the work done by gravity, well, that's going to depend on the force of gravity acting on this pile driver. This force of gravity is 1,860 times 9.8. So that's 18,228 newtons. So the work done by gravity, the force of gravity is down, it's moving downward. So it's going to be the force of gravity times the vertical distance, and it is positive because the force is down and the motion is down. If the force and motion are in the same direction, it adds energy to the object. And so the force is 18,228 newtons. The distance that the force of gravity acts over is not just the 8 meters. While the beam is being pushed into the ground, and it moves down an additional 0.25 meters, gravity is still adding energy to that. And then the beam is taking energy away as well, but work is being done by gravity over the entire 8.25 meters that it's traveling. So this distance that you need to use is the 8.25 meters. And then the work done by the beam is going to be negative. As this falls, again, I have this drawn up here, but when it hits, the force of the beam is upwards. So I have the force of the beam, but the beam is only pushing on the pile driver over that 0.25 meters. And so that's something that I can solve. I can take the 18,228 times 8.25 and set it equal to the force times 0.25. If I solve for the force of the beam, I get that it's 601,524 newtons. So again, this is a very large force that the beam exerted on the pile driver to stop it. It's an extremely large pile driver. It's stopping in a distance of 0.25 meters, which is a very short distance. So it's a very large force that acts on it. Again, if this is the force the beam exerts on the pile driver, Newton's third law also says that that's the force the pile driver exerted on the beam. That's why this pile driver is used to push this beam into the ground. It can exert a very large force on it, driving it into the ground. This final question. We have a person on ski patrol, and they're lowering a person down a hill. So the person with the sled has a mass of 90 kilograms. They're sliding them down a 60-degree slope at a constant speed. So if it's a constant speed, the net force is 0. The coefficient of friction between the sled and the snow is 0.1. So we're going to find the work done by friction. We're going to find the work done by the tension in the rope. We're going to find the work done by the force of gravity. And we're going to calculate the total work done. So first of all, we have the weight of this person. The weight is going to be 90 kilograms times 9.8 meters per second squared, which is 882 newtons. So then I can break that weight into components. This parallel component of the weight is 763.8344 newtons. This perpendicular component is 441 newtons. I have the normal force pushing up, which has to balance out the perpendicular component of the weight. So that's 441 newtons. The force of friction is the coefficient of friction times the normal force. The coefficient of friction was 0.1. The normal force is 441 newtons. So this gives the force of friction is 44.1 newtons. Okay, and to find the tension in the rope, we need to use the fact that the net force is 0. We're told that it's moving at a constant velocity. So it's sliding down the slope at a constant speed. So it's moving in a straight line at a constant speed, which is a constant velocity. It's not accelerating. So the forces acting up the ramp, the tension plus the force of friction, has to equal the forces acting down the ramp, which is that parallel component of the force of gravity. So the tension plus 44.1 newtons equals that parallel component of the force of gravity, 763.8344 newtons. So that gives me that the tension is 719.7344 newtons. Okay, so this is a problem where we had to use Newton's laws to figure out some of the unknown forces. Okay, so now we're looking at this person, and he's sliding 30 meters along the hill. So in part A, we're looking for the work done by friction. And so the work done by friction, he's sliding down the hill. The force of friction is up the hill. So the work done by friction is going to be negative. It's going to be the force of friction, 44.1 newtons, times the distance that it moves, 30 meters. So this work done by friction is negative 1,323 joules. Part B is how much work is done by the rope. So that's asking for the work done by the tension. Again, the tension is pulling up. So the work done is negative. So it's negative, and it's the force of tension, which is 719.7344 newtons. Times the distance of 30 meters, which gives a work done by the rope of negative 21,592.032 joules. Part C wants to know the work done by the force of gravity. Again, I could use the 30 meters and the 60 degrees to calculate what the vertical distance is, but since I've already calculated the component of the force of gravity parallel to the motion, I can use that to find the work done by gravity. So the work done by gravity is going to be positive because the force of gravity is the parallel component of the force of gravity is down the slope, and it's moving down the slope. And so I take that parallel component of the force of gravity, 763.8344 newtons, and I multiply by the 30 meters that it slides. And I get positive 22,915.032 joules. Okay, and the last question, we're asked, what is the total work done? So that total work done is going to be the work done by the force of friction plus the work done by the tension plus the work done by the force of gravity plus the work done by the normal force. We didn't calculate this one, but the work done by the normal force is 0 in this case. Again, the normal force is perpendicular to the direction it's moving. So if a force is perpendicular to the motion, it does 0 work. And so this net work was the work done by friction, negative 1,323 joules, plus the work done by the tension, which was negative 21,592.032 joules, plus the work done by gravity, positive 22,915.032 joules, plus the work done by the normal force, which is 0. And if you add all those together, you get that the net work done is 0 joules. And let's see if that makes sense. The net work done is the change in kinetic energy. It says that this is moving at a constant speed. So if the speed is constant, that means that the change in kinetic energy is 0. The initial kinetic energy and the final kinetic energy are the same. So if the net work done equals the change in kinetic energy, and the kinetic energy doesn't change, then the net work done is 0. Again, several of these problems related finding forces, finding friction, calculating the work done by individual forces, and in the end, relating that total work done to the change in kinetic energy. Again, there's a lot of other examples, but they're all along these same lines. So the most important thing is being able to identify the forces that are acting, being able to break those forces into components, and using those components to find the work done as it moves along some type of surface.